Welcome back to Pike Mathematics. Today I want to talk about permutations and combinations. When I first started thinking about making this video, I thought I'd just do a couple quick examples of each and move on to something else, but I thought about it a little bit and I decided I want to go a little deeper, particularly on the combination function. I want to illustrate how that function plays a critical role in the world of thermodynamics. I hope you enjoyed this video. Let's get started. As always, I'm going to open up a paper. Okay, we're going to talk about permutations first. Let's say I have three numbers, 1, 2, and 3. Here's a question. How many two-digit numbers could I make from this set? Well, I can make 12, I can make 13, I can make 21, I can make 23, 31, I can make 32. So it looks like I can make 6 unique numbers from that set. Now, each one of these is what we call a permutation. And the critical thing with permutation is that order matters. So 12 is not the same as 21, even though both have a 1 and both have a 2. They are distinct and unique. So there's a generalized formula for permutations where you have a set of size n, and you're trying to figure out how many subsets of size k you can make from that original set. And here's the formula for it. So the permutations are equal to n factorial divided by n minus k factorial. Now I'm not going to hit equals enter to kind of load this into iota because we already have this function p of n and k programmed into iota. So I just wanted you to be able to see what the function actually looks like. So we can test this right now. Let's go p of 3 and 2 with the example above. Let's see if we in fact get 6, and we do. What if we did 5 and 5? If you've got a set of 5 and you want to say how many different ways can you arrange those 5 elements? Let's see. The answer is 120 different ways. Again, for permutations, the order matters. Let's move on to the next thing, combinations. Let's say the order didn't matter to you. Let's say we had red, blue, and green. All right, these are our colors. And the question is, how many different ways can we pair these colors? So we could do like a red and blue. We could do red and green. We could do blue and green, but we're not going to say blue and red, right? Because we don't really care about the order. We just want to have these two colors together, and saying red and blue, that's sufficient. So there's a generalized formula for this too. And again, these are called combinations, and it looks like this. And it's C of n and k, and it's equal to n factorial divided by k factorial, put another parentheses in here, and n minus k, and then another factorial. And I close it out. All right. So that's the formula for combinations. And you see it's very similar to the permutations. The only difference is this k factorial. Essentially, what that k factorial does is it removes the duplications. It removes if you have red and blue, it removes the blue and red. So let's try that. Let's try that on the example we just did. So if we have a set of 3 and we want sets of 2, how many combinations can we get? Oops. There we go. It's 3, just like we wrote here. Well, let's try this example here, the 5 and 5 example, but in combinations. It's just 1, and that makes sense. If you've got a set of 5, well, how many different sets of 5 can you make where you don't care about the order? And the answer is just 1. Okay, so those are permutations, those are combinations. What else is there to discuss? For the longest time, I kind of looked at these functions as kind of novelties that just prepare you for the SAT. But in reality, they play a really critically important role in thermodynamics, and particularly the combination function. It helps us understand how and why heat flows. So let's start talking about that. Okay, let's look at a tab I created earlier. This graphic and all the other graphics I'll show later on in the video, I created using IOTA's graphing capabilities. IOTA has a pretty robust graphing suite. If you click on this graphic here, you'll see all the script. For example, to make this shape right here, I used our plotx function and I had a graph x squared. So when you get a chance, check out IOTA's graphing capabilities. Okay, Einstein solids. Einstein solids are a collection of what they call quantum harmonic oscillators, where each oscillator has quantized energy levels. And so here's kind of a, you oftentimes see the quantum harmonic oscillator depicted like this. What's kind of interesting is that the lowest energy level isn't zero, it's actually 1/2 h bar omega. And you can't move from 1/2 h bar omega to just anywhere. You have to move up in these steps, and these are separated by multiples of h bar omega. A real world example would be carbon in a diamond crystal. The carbon atom itself isn't the oscillator, but rather each carbon atom would have three oscillators associated with it, one for each uh, direction that it can independently vibrate. So let's look at some other graphics here. Okay, here we go. These little circles here, these are meant to represent units of energy. And right here, we've got the three quantum harmonic oscillators. A question would be, how many different ways could you arrange these energy units, sorry, into these oscillators? Okay. Well, here's one example. And the way to kind of read and understand this is that um, these these vertical lines are kind of separating the oscillators. So the first oscillator would have two energy units, the second one would only have one, and the third oscillator would have three energy units. Well, that's one way to arrange it, but there's more. You can do something like this where the middle one doesn't have any, and then the first and the third kind of split the energy units. Or here's another one. The first oscillator gets one energy unit, the second oscillator gets two, and the last oscillator gets three energy units. Now, each one of these possibilities, possible ways to organize the energy units, is what's called a microstate. Okay. What's kind of important to understand here is when you're doing an example like this, you have to think about, well, how many positions do I need in order to arrange these energy units? And obviously, you need a spot for each energy unit, and then you need a spot for all these partitions. But you don't need n partitions; you need n minus one partitions. So here we had three oscillators, and so we only need two partitions. So when you add all that up, in this example, we need eight kind of spaces in order to work through all the different combinations of ways you can place these energy units. Um, and so then the question is, when you have those eight spaces, how many different ways can you place these six energy units? Well, that starts to sound an awful lot like a combination problem, doesn't it? And it is. And it's I've written it out here. What it is it's the combination function where the kind of the big set you're working with is n minus one, because that's the number of partitions you need, plus the energy units. And then you're asking, well, how many different ways can you arrange those Q energy units into these spaces? This is oftentimes written out like this with this large omega, and this is called the multiplicity of n and q right here. And n and q represent what they call a macrostate. A macrostate where you have three oscillators and six energy units. And this is one of the microstates, one of the examples of how you could organize those energy units. So I went ahead and created this omega function and made it equal to this combination function that iota already understands. So I showed you three examples here of different ways you could organize those energy units, but how many total ways can you do it? Well, let's use that omega function. So I go backslash capital O and then lowercase me. That gives me omega. And how many oscillators do I have? I have three. And how many energy units do I have? I have six. Okay, there's 28 different ways that you can order these six units into the, what is it, eight total spaces that we have. And again, this is called the multiplicity, and the macrostate is three oscillators and six energy units. Okay, let's look at a little more complicated example. And I pulled this example from An Introduction to Thermophysics by Daniel Schroeder. It's on page 59 of chapter 2.3, problem 2.8. Here's the setup. We have two solids, solid A and solid B. And solid A has 10 oscillators, and solid B has 10 oscillators. And there are a total of 20 energy units to work with. And Schroeder notes that these solids are weakly coupled, and that allows for heat to flow from one solid to the other. Now, what the big question is how many microstates are there in this system? Another way of saying that is how many different ways are there to arrange these 20 energy units into these solids? To tackle this, I've created this table in IOTA. As you can see, I've already done quite a bit of work in it because I didn't want to spend the whole video creating a table, but we will do some portions of this together. The first thing we want to look at is solid A. And solid A, these are kind of the different energy scenarios for solid A. We start off with there's no energy in solid A, and then we go all the way down to all 20 energy units are in solid A. So the question we need to figure out right now is what's the multiplicity of solid A for these different energy states? Okay, so multiplicity, again, remember we've already defined multiplicity right here. It's a function of the oscillators in the total and the energy units, and then we've equated it to this combination function. All right, so let's start figuring out some multiplicities. We do equal backslash and the capital O, ME for omega, and the number of oscillators in solid A is N underscore A, because we've made this, we've already declared that here, so iota will pick that up. And then we need to reference the energy in this scenario, and that's this cell reference here, A2. Let's see what we get. Not surprisingly, the answer is 1. There's only one way to arrange zero energy in solid A. Let's figure out the other multiplicities. I'm going to copy this right here. So Control C and Control V to paste. And I think I've left a couple here that I have not filled yet. Let's do these two. Okay. So here are all the multiplicities for solid A. And you can see we go from this this state where we had no energy, and so there's only one way to do that. And then you go all the way down here. When all 20 energy units are in solid A, there's a little over 10 million ways to arrange that in those energy units. And you'll notice I already did the multiplicity for solid B right here. You'll see that basically they're just a reverse of each other. So when there's 0 energy units in solid A, there's 20 energy units in solid B. So the next thing we need to do is we need to find the total multiplicity for the system when for these macro states. Here's a macro state where we have 0 energy in A and 20 energy units in B. What's the multiplicity for that state? And that's just if the product of omega A and omega B. I've already put that equation in here, but I do need to essentially refresh the page because I just added this information. So I'm going to refresh it. Takes a little time because it's essentially refreshing everything that I've got here. There we go. So here's the total multiplicity. You can see at either ends we get that 10 million number. But then at the greatest multiplicity is when we have 10 energy units in solid A and 10 energy units in solid B. Well, let's see how many total microstates do we have. Iota has a nice sum function. We'll just reference these cells. It looks like E2 through E22. See what we get. All right, this is a big number. Looks like it's a little under 69 billion ways to arrange those 20 energy units into these two solids. Another thing that's worth looking at is kind of what's the probability of a macro state. And so if I take the multiplicity of any state and then divide it by this 69 billion number, that gives me the probability. And that's what I've done in this column right here. And you can see, again, the most likely outcome is the 10 energy units in A and 10 in B. But that's only 12%. These other scenarios where it's 9 and 11 or 11, 9 are pretty close in probability. Let's go ahead. We have a function in IOTA that will graph data from tables. So we're going to do that. I've already created a grid here. All I need to do is hit insert function, and I want to use this um, poly table function right here. Okay, so what I need to do is tell it what information to graph, and already it's looking at row 2 through row 22. That's correct. And then the x-axis, I want the x-axis to be these energy levels. That's right. And then the y-axis should be these probabilities. Okay, that looks right. I'm going to change the origin to 0, put it in blue. Let's graph it. There it is. So this is the graph of this data right here. And again, you can see that the the highest probability is when we have 10 energy units in each solid. What I would tell you is that we are working with relatively small numbers here, 10, 10, 10, and 20. Real world examples will use much larger numbers, things like 10 to the 23rd and larger. And when you do that, if you were to graph that information, you would essentially make this peak. This peak would become much more prominent, and then the rest of the graph would kind of get pushed down almost to 0. So it would look something like this. Very low probability, very low probability, and then some boom, you get a sharp, almost needle like graph, and then the rest of the graph would then kind of go back to 0 again. But this is because we're using these small numbers. Okay, it's time to talk about entropy. Here's the definition of entropy. Entropy is often depicted with an S, and it's equal to the Boltzmann constant times the natural log of the multiplicity. Entropy is one of those concepts I've always had a little trouble grasping, and I never found vague definitions that use words like disorder or chaos all that helpful. I prefer just this mathematical equation, which tells us that entropy is a function of the multiplicity, or the number of microstates in a macrostate. So let's look at entropy with respect to the example we worked on earlier. So I'm not going to actually figure out the entropy. I'm just going to figure out the natural log of the multiplicity is. But that only differs by the Boltzmann constant. So it's basically telling us everything we need to know about the entropy. So I'm going to work on solid A first. So I'm going to go equal ln, and then the multiplicity of solid A. Here it's in this cell B2. Okay, 0. Okay. Let's see what it is for the other energy states. Copy that. There we go. Okay. So let's kind of look at what happens here. When we went from 0 energy in A to 1 energy unit in A, what happened? Well, that the natural log function went up significantly. It went from 0 to 2.3. But look at look at what happened for solid B. Solid B decreased, but very little with respect to the gain in A. So the decrease in B is something like, I don't know, about 0.36 when A gained 2.3. I think it helps for something like this to actually look at the natural log function to kind of gain a better understanding of what's going on. So we're going to go ahead and go to plot X, graph the natural log function. Make it red. There we go. All right, let's say we've got, again, we've got two solids, and we've got a solid over here that has very little energy, and we've got a solid over here that has much more energy. What happens when just a little bit of energy from this solid flows to this solid? Well, the short answer is that the entropy for this solid goes up, and it goes up much more than the entropy goes down for the solid over here. And that you can see that by the curve of the natural log function. And so let's look at what happens to the other scenarios for our example. You can see that A continues, as long as you put more energy into A, it's gaining entropy. And as B loses energy, it's losing entropy. But until you get to about this state, when you get to where there's 10 units in each, the net gain in entropy is positive as energy flows from solid A to solid B. But once you get past that, it is if energy were to still flow from B to A, the system would lose entropy. And this leads us to the second law of thermodynamics. It tells us that a system in equilibrium will be in the macro state with the highest multiplicity. That is the most probable state. And because we know how entropy is defined, this is equivalent to saying the system in equilibrium will be in the macro state with the highest entropy. This is rather profound and explains why heat flows from hot things to cold things. When those energy units flow from the warm things to the cold things, entropy increases, and they will continue to flow. Heat will continue to flow from hot to cold until there is no entropy to be gained. This is all very profound. And right there, right at the heart of this, is our little combination function that we talked about in the beginning of this video. In reality, though, when you work with these really, really large numbers, you can't actually use the combination function as it is, and you need to start approximating it. But regardless, what you are approximating is the combination function. So it definitely is not a novelty function. I hope you enjoyed this video. I am planning many more, so be on the lookout for those videos. Please visit us at pikemathematics.org and give IOTA a try. Email us at support@pikemathematics.org with any questions or concerns. Thank you for watching.